Hello everyone, welcome to the new video on sample size calculation. Before you begin any of your research, you have to calculate the sample size to estimate the power and the alpha error of your study. There are multiple sample size calculation formula that are available. One of my favorite references is the fundamentals of biostatistics. And when you look at the sample size formulae, you have different formula for different comparison or correlation that you have to do. You can have sample size calculations for means, paired means, correlation coefficient, proportion, and so on. Let's have a look at all these formula and what they mean. These formulae are used not only manually but also by various softwares like GPower, PASS, NMaster, which are used for calculating sample sizes. These formulae are also used by online calculators like calculator.net, openap.com. Let's have a look at these components of the formula. Let's focus on the first variable. Whichever formula you take, there are two z values. And the highlighted one here is the z function of an alpha. Next, each of this formula will also have a z function of beta. Then you can see that there is a sigma. So as you can see here, there's a sigma here, which represents the standard deviation. Here, instead of sigma, we have used the symbol S, which does happen in certain formulae. Some may not have the standard deviation. Instead, they will have the proportions, like you see in this formula. The last component is the difference in the mean or the proportion. So if you look at these variables, usually represented as D. So let's understand these components first. I would bring to your attention an article on principles of sample size calculation. I will leave the link in the description below. Let's have a look at the first two variables, the Z components. These Z components are nothing but constants. These constants are similar to that of the log tables that we use. For example, log 2 to the base of 10 is 0.3010. Similarly, earlier days, before the advent of softwares, these Z functions were actually referred to in a book or a constant tables that were available. What does these constants mean? Let's have a look at the first constant, the alpha. Alpha, also commonly referred to as the alpha error, is representing the false positive error. When you look at a null hypothesis, we say that when there are two groups, there is no difference between the two groups. This is what null hypothesis states. What happens if the test or a comparison that you're doing says that there is a difference when there is actually no difference existing between the two? What I mean is, if a significant difference is noted where it should not really exist, it is a dangerous situation, especially in a clinical practice. So this kind of error should be least. So we conventionally set it as low as possible, usually at a 5%. So that means 95% of the times this event has occurred because of this particular intervention. You are ready to leave only this particular component of alpha for chance. Usually it is 5%, but if you keep it at 1% or 0.1%, it becomes stronger. Let's have a look at these two formulae again. When you set an alpha error of 1%, the z1 minus alpha by 2 will become 2.57. When you keep an alpha error of 5%, it becomes 1.9599, which is usually rounded out as 1.96. So if you look at these, who chooses these alpha errors? It is the investigator who chooses the alpha error. The investigator decides how strong you want your results to be. Similarly, once the alpha error is chosen, the corresponding p-value becomes your set level of significance. So suppose you keep an error of 5%, then your p-value will be set at 0.05, which is the conventional state. But if you set your error at 1%, your p-value will become 0.01. Let's look at the beta function. Beta function is the different function in which we are looking at a probability to reject a false null hypothesis. It's also called as the beta error. What does it mean? It means that the probability of not finding a difference when actually one exists. So in reality, there is a difference between the two groups, but your test is showing that there is no difference. This is not as serious as that of an alpha error. So if your test says there is no difference, but in reality there is a difference, this is not a good thing for a screening tool. The function 1 minus beta is usually the power of the study, which you want it to be as high as possible. Conventionally, it is kept at 80% and above. Now, when you're looking at an 80% or above power, you have these constants for Z1 minus beta. 80% gives the value of 0.8416. 95% gives the Z1 minus beta as 1.64. Who chooses this again? This is again chosen by the investigator. Once the investigator chooses the alpha and the beta, you are ready to go to incorporate the same in the formula. Let's look at these constants a little more closely. As the alpha reduces, the Z1 minus alpha increases. As the power increases, Z1 minus beta also increases. Now these two values are sitting on the numerator. That means as you improve your power and reduce the alpha error, your values of the sample size are going to increase, as both these constants are present in the numerator. Let's look at the third entity, the standard deviation. These standard deviations are the ones which you have to search in your key article. Usually the primary aim is decided and the sample size calculation is done using the primary aim. You may have multiple variables involved in your study. Even if you have 10 different variables, one of them should be considered and decided as the primary aim. Once the primary aim is chosen, search for a key article in which this primary aim measure is calculated. If you have two groups, we need the values of these two groups. It can be the mean values along with the standard deviation, or it can be proportions. But there does occur a situation in which the study is new and the research using these materials or parameters are not done. In such a case, you have to do a pilot study. This pilot study does not have a set sample size. You can do it as your convenience or feasibility or finance allows, and once you get the results of the pilot study, which will have a particular standard deviation or variation that is seen, that can be used to calculate the actual sample size. Let's understand this a little more detail. This standard deviation is represented by sigma or S most of the time, as this is also placed in the numerator. Higher standard deviations usually yield higher sample size. Why is this so? Let's understand this in a simple example. Let's see the bar graph in which there is a group of males and females whose height has been measured. As you see here very clearly, the females have a lower mean height than that of the males. Now, is this significantly different? It does look different, but let us incorporate the standard deviation into this same setup. So when you incorporate the standard deviation, you understand that the variation of the mean values is in this particular range. So let us say that this is the said standard deviation. You can see that there is no overlap between the lowest value of the male and the highest value of the female heights. Thus, these two are definitely significantly different. Let's look at a slight modification of the same scenario. Let's increase the standard deviation. When you increase the standard deviation, you can see that the lowest value of the male and the highest value of the female height has an overlap that indicates that this may not be statistically significant. So what does this mean? The higher the standard deviation, You need a higher sample size to prove the test difference. Thus, it is important for us to identify the standard deviation that you are expecting from the key articles or the pilot studies. Now let's have an example, how to get the standard deviation from a key article. So here is an example article which I have picked up. When you look at this particular key article, you can understand that there is a comparison between two drugs here. And what are they measuring? They are measuring some amount of post-operative analgesia. So if you scroll down and read through the article, you will realize that your primary aim is actually the mean time to uh, give a particular analgesic. So the time is usually in minutes. So you'll have a mean and a standard deviation that will be there. And you keep scrolling down and figure out, look at the tables and the results, and you will find this particular table here. So here you can make out that the two groups have two different means and standard deviations, that is the time to first analgesic requirement. Now if you look at these tables closely, you will realize that the standard deviations are 1.04 and 3.64 respectively. If you add it up and divide it by 2, that is if you average it, you will get a standard deviation average, that is sigma, of 2.33. Once you get 2.33, you see that the difference between the two means, that is 1.6 minus 0.33, is 1.27 units. Now, does that mean this is the D value that is there in the denominator? Not exactly. This unit 1.27 should be clinically relevant also. Now, who decides this? The investigator or the clinician or the expert has to decide this. You cannot blindly take the difference between the two means that are observed in the key article as your D value. So you may have to introspect a little more into the variables and understand whether this much difference between the two groups is clinically relevant. To put it into perspective, if suppose you are using a new technique and which is reducing the time taken, will you stop using the technique which is taking 1.27 minutes extra just because the newer technique is faster by 1.27 units? A difference of 5 heart rates may not be clinically relevant in some medications which reduces the heart rate, but a difference of 5 millimeter may be very essential for some studies in which you are measuring nanometers. So you need to understand what is the difference, and you need to give the statistician the difference that you are expecting to be clinically relevant, which is the value of D. Let's have a look at another example. In this case, we'll look at some proportions. So here we have an article in which there is platelet-rich plasma used for post-operative quality of life. Now, when you look at the post-operative quality of life, there are multiple variables. Now, when we had discussed with the investigators, they told us that the presence of bleeding itself is a poor quality of life. So what exactly are we looking at? We had to search for the article and the relevant table, and then we figured out that out of 25 patients, that is 22 plus 3, 25 patients, 3 had bleeding in PRP group, whereas the control group had 11 individuals who had bleeding present. So these are the parameters that we will be looking for to calculate the sample size, 3 out of 25 and 11 out of 25, which when calculated as proportions and put into this particular formula, you will realize that 0.12 and 0.44 are the P1 and the P2 values. Hence, you need to be careful what you are giving to the statistician. So the statistician is actually expecting you to tell them the alpha, that is, what is the alpha error or accuracy that you're looking for. Conventionally, it is used as 5%, but if you are really looking at a stronger study, you may request for a 1% alpha. The power of the study has to be higher. The power is actually 1 minus beta. So you're looking at a beta function here, and when you're looking at a power, it is conventionally kept at 80%, but you do have to communicate to the statistician what is the power that you're looking for. Is it 80, 90, or 95? Some even request for a 99% power. The standard deviation has to be searched in the key article and highlighted before you submit to the statistician so that he is able to understand. Most of the time, the statisticians are not from your relevant field. Hence, it is mandatory for you to highlight the article numbers for them to calculate the sample size. The difference in the mean or the proportion also has to be expressed to the statistician. You have to decide what is the clinical relevance or the difference that you are expecting, which can be either in mean numbers or percentages. So with this background, we wish you best of luck for your research ahead. I hope this particular video helped you understand sample size calculation, and finally the sample size calculation is decoded. Thank you.